Hello, and I would like to perform a resistor network with multiple batteries and real batteries, although ideal wires, direct current system where we have to use Kirchoffs laws to really help us to solve this problem. So we'll be using both the junction rule and the loop rule. So let's have a look at our circuit. Notice that each EMF is labeled with a capital E and a subscript. Each battery, which includes the EMF and the internal resistance, has a small r, which means the internal resistance of each battery, each of which is pretty small. We also have 1, 2, 3, 4 load resistors. That's capital R1 through capital R4. And we have electric current, of which the directions are labeled. Okay, so let's go ahead and start writing down Kirchoffs rules. So first, by the conservation of charge, we have Kirchoffs junction rule for electric current. So again, for electric current. Okay, so this should be the following. It should be I1 comes into junction B, so the junction points are labeled with lowercase letters. So I1 comes into junction B, and looks like I2 and I3 go out. So that means I1 should equal to I2 plus I3. That's conservation of charge, conservation of current. All right, that looks just fine. Let's in fact call that equation 1. Now, what we also need to do is we need to create equations for Kirchoffs loop rule. So again, Kirchoffs loop rule for voltage. So when we perform an entire closed loop on a DC circuit where each wire has a uniquely defined resistance, the total voltage drop around a continuous loop should be 0. Okay, continuous closed loop. Well, let's go ahead and label some loops, shall we? Looks like black, red, and blue are already used on this diagram. So I'd like to switch to green for our first loop. And if possible, I'd like to go with the current that's already on there, so things work in a somewhat traditional way. So why don't we go from spot F all the way around the left-hand loop clockwise back to spot F. So let's go this way in terms of our loop. So let's go F to F. So let's say F, whoops, F to F clockwise loop. Okay, so let's work this out. It should be the first EMF and then minus, we're going with the current, and the current should be I1 on this piece. So it should be I1 times R1, little r1. That's the internal resistance of this battery. Then we get to junction point A, we're still on a wire, and now we're still with current I1, and we're multiplying it by R1. So it's minus I1 capital R1, that load resistor. Then we reach junction point B. Then through the middle branch, we're on current I3. But then we go through resistor 2. So then we go minus I3 R2, and then we go across this battery in the correct direction from the negative to the positive terminal. So that should be plus epsilon 2, and then minus this internal resistance, because we're going with the current, I3, so it should be minus I3 R2, And then we should go this direction, and again we're back to I1, but for the current, but we're going the correct direction across this resistor, so that should be, in order to get an energy decrease, so it should be minus I1 R4. And that should equal to 0. Okay. Let's do an even different color for the last loop we need to do. Oh, and by the way, this should be equation 2. Because we're going to need, I think, there's 3 unknowns, there's 3 unknown currents, so I think we're going to need 3 equations to solve this linear system. So now, let's do our final loop. So our final loop, I think, again, we have choices as long as it's a continuous loop. So what we could do is we could go all the way around the outside if we like. And that would work just fine. Because, especially if we go all the way around the outside, we're generally going with I1 and we're generally going with I2. So maybe why don't we go this way, all the way around the outside. So all the way around the outside. So now let's go F to F clockwise outer loop. And by the way, just to be clear, that previous loop was really the loop on the left side. Okay. So now, if we're going to do the outer loop clockwise, F to F, let's see what that gives us. Okay. So let's start. Now notice, we should have the same result for these first 3 devices as we had right here. Because we should have an EMF 1 across internal resistance of the battery, lowercase r1, and then across this load resistor, capital R1. So that should be EMF 1 minus I1 little r1 minus I1 big R1. Okay, good. But now we're going to go on the outer branch. So we're going to go from B towards C. We're going to go across resistor 3 with current I2. So it's going to be minus I2 times R3. Then we go across this battery in the correct direction because we're going from the negative to the positive terminal. So that should be plus epsilon 3. Then we're going with the current, that is I2, because I2 is on this entire section, the entire right-hand part of the wire, if you will. And then we're going across R3, lowercase r3, so that's minus I2 R3. And then we're going across internal resistance of this battery 4, so that's minus I2 lowercase r4. And now we're going the wrong direction across this battery because we're going from a positive to a negative terminal. So that should be minus EMF 4. And we're back to junction point E. And this last part should be the same as this last term here of the first loop because we should go across R4. So it should be minus I1 R4 equals 0. And that's our third equation, equation 3. Okay, now this looks like a big algebraic mess, especially the second and third equations. But now let us consider our plan of attack. Okay, the reason I say plan of attack, so to say, is because we want to be able to simplify these things. Okay, so first of all, equation 1 is not too difficult. All the coefficients have magnitude of 1, but we want the other terms to be moved to the left-hand side. We'll get to that on the next board. Secondly, regarding equation 2, we should be able to add these EMFs together. And then notice, anytime a current is in more than one term, I'm going to underline it. So I think that current 1 is here. It's also here. And whoops, here. And I also think it's here. So we should be able to put all those terms together because they all have the unknown variable I1. In fact, one thing I probably should write down while I'm thinking of it, just to make sure this problem is clear to you the viewer, I1 and I2 and I3 are the variables that we seek. Those are the unknowns. Because we were told at the beginning, find the currents in the following circuit. Okay. So, moving on from there, we say fine. Let's circle these because these EMFs should go together. Alright. Let's do any I3s in a box. Fine. So those terms should go together. And then let's do the same sort of thing in this third equation. That's the second loop rule equation. So here's a couple EMFs. And I think there's also another EMF over here. So we got to put all those together. Anything that's current 1, I1, I'll give a single underline. Single underline. Single underline. And then back here, single underline. Now that looks exactly the same as here, so they should get the same number on this I1 term. Now I2 we haven't done yet, so I'll do the squiggly underline. So these are all I2 terms, where we go across resistors. So the key is we need to be able to clean all this up. Now, I'm going to be toggling back and forth between this blank board and this board in order to get things correct. So let me see how I can do this. So I'm just going to work on the left-hand side of the loop rule equations first. And by the way, I'm going to rewrite equation 1 to start here. So I think it's going to be I1, well, I'll just write 1 I1 equals 1 I2 plus 1 I3. So that's equation 1 becomes 1 I1 equals 1 I2 plus 1 I3. Fine. It's equation 1. Now equation 2, let's add these EMFs. So that's EMF 1 and 2. And they're both pluses. So that should be 18 plus 3 volts. Okay? So again, 18 plus 3 volts. So this should be, starting equation 2, 18 volts plus 3 volts is 21 volts. And the next thing is we should do the I1 terms. So that's, let's see, lowercase r1 is 0.5, and then 20, and then 15. So let me write that down. 0.5, 20, and 15. And they all have minuses. So it should be minus 0.5, 20, and 15. Okay, all of that times I1. Then we should also have a plus, I think, 0 I2, because there's no I2 in this equation. There's no current 2 in this equation. Plus 0 I2. And then for current 3, that's these two terms, capital R2 and capital R lowercase r2. So that's 6 plus 0.25. And again, they both have minuses. Minus 6 plus 0.25 times I3. And again, that should equal to 0. Okay, how about equation 3? Okay, so equation 3, first of all, we should add the EMFs. So that should be, let's see, 18 volts and then 12 volts. Those are both added. But then we have minus EMF 4. So that's 30 volts minus 24 volts. So actually, I'll just write that down. So that's 18 plus 12 minus 24. Okay, we'll come back to that very soon. Then, let's do the I1 terms. Now, the I1 terms should look exactly like the previous loop, because the parts of the resistors that we looped on were the exact same ones. So I should just be able to recopy that if I was careful. So that should be minus 0.5 plus 20 plus 15 times I1. Okay. Now, as far as I2, the squiggly underlines, we've got big R3, little r3, and little r4. So that's 8 and 0.5 and 0.75. And those all have minuses because we're going the correct direction with the current. So 8, 0.5, and 0.75. So minus 8 plus 0.5 plus 0.75. And that's all times I2. And I don't think there's any I3s, no boxes, correct, in the third loop the third equation, which is the last loop equation. So that's going to be plus 0 I3 equals 0. Okay, so let's clean these equations up. So let's try to make 1 look as nice as we can. Let's line up the I1, I2, and I3s and put all coefficients on the right-hand side. So this is 1 I, and let me actually change to white so that you can see a little better. You, the viewer. Okay. So let's see. This is equation 1 becomes 1I1 minus 1I2 minus 1I3 equals 0. That looks fine. Then the second equation. Now the second equation should be that 21 had to go to the other side of the equation. So that should be negative 21. Then the I1 should be 20 plus 15, that's 35, plus 0.5, that's 35.5 with a negative. Negative 35.5 I1 plus 0 I2, and then this is 6.25 minus 6.25 I3. And then lastly, the third equation. So 18 plus 12 should have been 30, minus 24 is 6, and that got moved over to this side. So that's minus 6. Then, again, this I1 term is exactly the same, so it's minus 35.5 I1, and then I2 is going to become, let's see, 8.5 plus 0.75, that's 9.25, so minus 9.25 I2, and there's no I3. And that's equal to that negative 6. Okay, So now what we should do, is we should set up this rectangular array of numbers. So I've set up a matrix with an augment, and the augment is separated off by this dashed line to recall that the right-hand side over here is just what's to the right of the equal sign. So let's put in our coefficients. 1, -1, and -1. Let's put in -35.5, 0, and then -6.25. Then let's put in -35.5, -9.25, and then 0. And then now let's put in our solutions over here. That is our augment. So it's 0, -21, and -6. Now, the matrix solving should give us our currents. It should give us I1, it should give us I2, and it should give us I3. So let's see if we can indeed solve. Okay, let's go to the calculator here. All right. So, on, and let's clear. So let's go over to second matrix, and let's go over to edit. Now we can edit matrix A, or we can edit matrix B. It doesn't really matter. Why don't we just edit matrix B? This matrix should be 3 rows by 4 columns. So there's 3 rows. The first by convention is rows, and the second part of the dimensions is columns. So we should be able to type the coefficients in. 1, -1, -1, 0, and then -35.5, 0, -6.25, and then -21. Then -35.5, -9.25. If we just want a 0, we should just be able to hit enter, because by default those are zeros. So just enter, and then last entry should be -6. Okay, so now we should do second quit. Now we need to operate on this matrix and reduce it to get the solution. So let's do second matrix and go over to math, and we can scroll from the bottom if you like. You can go reduce row echelon form, enter, and then we need to input our matrix. So second matrix, and let's go down to matrix B, enter, close the parenthesis, enter, and then there we get our solutions. So let's write these down. 0.381. So we should get, let's see, 0.381 amperes. We should also get -0.814, -0.814 amperes. And then finally, we should also get 1.1, so pretty close to 1.20 or so. So 1.20 amperes. Now, this minus means the current is actually in the opposite direction from what is labeled. So really, if we go back to the diagram, I2 is in the wrong direction. So since I2 is in the wrong direction, it's really I2 is not going this way, like clockwise. It's actually going counterclockwise on this segment. So it's really I1 plus I2 equals I3. So it's really I1 plus I2 equals I3. So sort of like really, in terms of the real directions. But anyway, that wasn't necessarily clear to us until we started working this problem. And then these are the magnitudes of all the currents. This is what we wanted to solve for. Where this minus sign only tells us it's the opposite direction. And this solves the Kirchoffs laws problem. I hope that was helpful. Thank you very much for your attention. Please smash that like button if you enjoyed this content and it's helpful and useful to you. Please subscribe to the channel to grow the channel. Please share this with people within your sphere of influence, and I will plan on seeing you in the next video.